Welcome back to our electromagnetic lecture series. In today's session, we will be dividing into one of the fundamental concepts of vector calculus, curl, and its application in Ampere's circuital law. We will begin by applying Ampere's circuital's law to the perimeter of a differential surface element, and then we will introduce a special vector called as curl, which is a derivative of a vector, and then we go for the point form of Ampere's circuital law. Then we will solve a numerical example and take some homeworks. So let us quickly recall the Ampere's circuital law as seen in our previous video. Okay, so it states that the line integral of H about any closed path is exactly equal to the direct current enclosed by that path. The equation is shown on the screen. So with respect to this Ampere's circuital law, what we will try to do now is we will take a differential surface, okay, whose sides are given by delta x and delta y. This is in the air parallel to the floor. Now let us say because of some current at the center we get a magnetic field intensity which is given by H naught. Now how do we define this H naught with respect to the differential surface? Is by applying this closed integral H dot dl for all the paths of this differential surface. Now first let us see to do this H dot del L to the side 1 to 2, that is for the path 1 to 2. Then let us do it for path 2 to 3, then 3 to 4 and 4 to 1, and add them together gives us the closed integral H dot dl, which is nothing but the current enclosed in that particular path. So let us see the first part, H dot dl for the path 1 to 2. So now what happens here is, this is nothing but the magnetic field included in the y direction, y component from path 1 to 2. That particular magnetic field multiplied by the length, which is delta y. Now the question is, how do I identify that particular magnetic field? Because we don't know the throughout magnetic field, we know the magnetic field only at the center, which is H naught, and the y component of this H naught can be described as Hy naught. So the x component of this H naught will be Hx naught, Hy naught and Hz naught. Now as we come towards the positive x axis or positive y axis, what happens to this incremental surface is shown here. So in the y direction, the magnetic field is Hy naught plus the variation what we get in the direction x. As we move away from this, the variation will be dou by dou x, the rate of change in x direction of this y flux multiplied by the distance what we encounter. Now the total distance here is delta x, but this dot is at the center, so we consider that distance as half times the x. So this particular equation what we have is only for this Hy of 1 to 2. Now this particular component is to be multiplied by delta y in order to get HL 1 to 2, which is shown by the equation in the yellow color. Let us glance this equation and try to understand it for 5 seconds. So what we did is, we have a dot at the center which is nothing but a magnetic field which is given by H naught. This H naught can be resoluted into Hx naught, Hy naught, Hz naught. as shown in this particular equation. Now we know only the magnetic field at this particular dot. Because of this, we try to find the magnetic field in y direction from 1 to 2, which we define it as Hy from 1 to 2. How this Hy from 1 to 2 is obtained? It is the center magnetic field whatever is present. For that there is an increment by this particular component. What is this particular component? The Hy component varying in x direction, rate of change in x direction, because from the center this 1 to 2 is in the positive x direction. So the rate of change will be dou by dou x. Okay, so this dou by dou x, we travel to a distance of how much? Half times delta x. Why? Because 1 to 4 the full distance is delta x. From center to this 1 to 2 the distance is half times delta x. So this is that Hy of 2. So H dot del L from 1 to 2 is given by the equation given here. Similarly, now we have to find this H dot dl for 2 to 3, 3 to 4 and 4 to 1. So we have the equation for H dot dl for 1 to 2. By applying the similar logic, we get it for 2 to 3. Now in 2 to 3 what happens? The magnetic field is in minus x direction. Okay, but we know only the x component at the center, which is Hx naught. So this is to be added with the x component varying from here to here, which is in positive y direction. So rate of change is dou by dou y for a distance half times delta y. Overall this entire thing is negative because it is in h direction, and the length expended from 2 to 3 is delta x. So this is the differential volume element. So now from 3 to 4 and 4 to 1, how it will be, that is to be found out. Overall, when you find this 1 to 2, 2 to 3, 3 to 4 and 4 to 1, okay, 3 to 4 and 4 to 1, overall when you find this, we have to do this closed integral h dot dl, which is nothing but adding everything, we get the answer as shown here. So this is true for the given case. Now as we know that magnetic field is to be related with respect to the current, this h dot dl what we have is nothing but the current, which can be told as current density multiplied by the area, which is nothing but delta x delta y, which is having a current density Jz in the given area. So now this h dot dl divided by the given area will give us the current density, and as this area shrinks to 0, the magnetic field itself will become the current density, which we get by applying the limits. Limit delta x comma delta y tending to 0, closed integral of h dot dl over the area delta x delta y is Jz. This is that Ampère circuital law what we have in the differential surface. So this equation what we have can be on the other way also, that is if the area is in y and z, we get the equation as shown, and if the area is z and x, we get the equation as shown. Now overall this differential surface what we have, if it is present in the 3 dimension, then all the x, y and z components are to be included. So the definition here, the component of the current density is given by the limit of the quotient of the closed line integral of vector h about small path in plane normal to that component and of the area enclosed as the path shrinks to 0. So considering this definition, we call this as curl in vector calculus. So that is limit area tending to 0, the quotient what we get by dividing the closed line integral about a small path what we have, this becomes the So now in our given figure we see that the current is in z direction for xy area. So the curl what we have, we define it in the normal direction to the given area. So in the rectangular coordinate system, the curl of H is given by ax, ay, az vectors, that is the x component plus y component plus the z component. So we see here the x component is dou by dou y of hz minus dou by dou z of hy. This is in the x direction, so we use a unit vector ax. So this is in the y direction, so we introduce a unit vector ay, and this is in the z direction, we use a unit vector az. So this is the equation for curl of H in the x, y, z coordinate or the Cartesian coordinate system, which can also be written as determinant of the matrix that is shown on the screen. Now when you expand this particular determinant, you get the same equation, and this curl of H is mathematically written using the symbol del cross H, where we know the del operator already, which is dou by dou x. So curl is given by represented mathematically by this. Now this is the expression for the curl in cylindrical coordinate system, and next we shall see the expression for the curl in the spherical coordinate system. So considering what is the application, a particular coordinate system can be selected and curl of H can be evaluated. So just by writing this particular determinant and solving this determinant gives us curl of H, which is nothing but H dot dl, line integral, divided by the area, and thus it is possible for us to find the current rather than evaluating the H dot dl entire integral. So this is the application of vector calculus in electromagnetics. Let us try to understand this particular example, how complicated it is to find H dot dl by the traditional method and how easy it is by using curl. So what we are trying to do in this particular example, now there is a magnetic field H vector, okay, which is defined as 0.2 z square in the direction ax. Okay, so this is vector H, which is 0.2 z square in the direction ax, and everywhere else this vector is 0. Only in the x direction it is 0.2 z square ax, all other direction the magnetic field intensity is 0. Now there is a perimeter given whose sides are D and D. The center of this perimeter is at distance 0, 0, z1. With this given parameters, what we have to do is we have to find H dot dl for each side, add it, we get H dot delta L, and then understand what is closed line integral H dot dl. So let us take one side at a time. So if we consider the top side, okay, which is 0.2 z square ax. What is vector H? Vector H is given by 0.2 z square ax in the x direction. Now what is the value of z here when I consider the top element? When I consider the top element, this is z1, this entire term is d, so from the center to this one becomes d divided by 2, and this where this top path is present, this will be present at a height of z1 plus d divided by 2. So this will be the value for z in this particular equation. So considering that equation, for z square what we have to substitute is z1 plus half d whole square. This will be h, okay, 0.2 z1 h multiplied by the length, which is delta L, which is given as d. So this is h dot delta L for the top line. Similarly, we have to find this for all other sides. So now considering this downside, we have to find h dot dl. We know that dl is d, but h as told only in x direction H is present. This is downward z direction. H should be 0. So, H dot delta L there will be 0. Third way, we see that H is present in the negative axis, which is given to us in the equation 0.2 z, and we take it here. Now, this is half d, the distance what I marked, and this total distance is z1. So, the remaining distance where this lower line is present will be z1 minus half times d square, and this is in the negative x direction. So, we take a negative sign. And lastly, the fourth one, distance d is in positive z direction, and as per the given instruction, in the positive z direction the h is 0. When we add this everything, we get h dot dl as 0.4 z1 d square. Now, from this, as per our definition, curl of h along the y axis is limit d tending to 0, h dot dl divided by d square, which is limit d tending to 0, 0.4 z1 d square divided by d square area. So, d square gets cancelled, we get 0.4 z1 as the answer, as the limit d tends to 0. Now, the same value we should be getting it with the help of the determinant what we have. Let us verify. So, the application of the curl says us that we should get the same answer, that is del cross h should be 0.4 z1 ay in the direction y by using the determinant. So, let us see the determinant. Del cross h is given by this particular determinant. Let us substitute the known values here. Now, the h is given as 0.2 z square in the ax direction, which becomes the hx component. Hx component is 0.2 z square. Hy component is 0, hz component is also 0. So, the determinant is like this. Let us expand this determinant, which is in the ax it will be 0, in the ay direction it will be dou by dou x of 0, which is 0, minus dou by dou z of 0.2 z square. Okay. And in the az direction, pay a careful attention here for the determinant. In the az direction, it will be dou by dou x times 0, okay, which is 0, minus dou by dou y of 0.2 z square. Now, with respect to y, z is constant and the differentiation of constant is 0. So, that term becomes 0. We will be left out with only ay term, which is 0.4, that is 0.2 z square differentiated with respect to z, we get it as 0.4 z ay. And what is the value of z here at our given point? The value of z at our given point is z1. So, when we substitute it, we get 0.4 z1 ay. So, this is the application of vector calculus. Instead of finding the entire h dot dl one by one and adding it, simply substitute the known parameter in the given determinant and get the answer. With this concept, let us take a moment to solve these two numericals whose answer is already given in the textbook. Let us not forget that the notation what is used in the textbook is the bold letter h signifies it is a vector. Wherever there is a bold letter h, let us understand that it is going to be a vector. So, kindly apply the given concept and solve this particular numerical. The answers are given. The detailed step of this particular numerical will be explained in the next video. So until then, please stay subscribed. Thank you.